Let's get into Unit 2. Unit 2 is about research methods. Traditionally, it is a higher percentage of the exam, with the traditional makeup of the exam being 66% multiple choice questions. Unit 2 is 8 to 10% of those questions, so anywhere from 8 to 10 questions, and it's actually one of the two FRQ questions, so it is a big percentage of the exam, and it's pretty foundational in psychology because it's research methods, but luckily it's things that you've seen extensively before, and so we'll review the various ways that psychologists do research. First, you have the scientific attitude. It's pretty simple. It's the idea that you are supposed to evaluate things from a scientific standpoint, which means that you analyze the fact that we have biases. We're trying to avoid confirmation bias. We're trying to avoid hindsight bias, and we do so by using critical thinking, and that's evaluating the evidence that's there. There's a famous phrase in scientific research that says observation is not evidence. So even when we see something that we think is evidential, we have to actually test it in a lab setting against a control group, and we have to try to eliminate confounding variables and analyze data so that we can come to a scientific, reasonable conclusion to support our theory or our hypothesis with evidence, which can be problematic. As we'll see in a minute when we get into the other ways that people do field research when experiments are not necessarily possible or ethical. So when you look at the throwback middle school science classroom posters here that you see on the screen, you see the scientific method laid out. Basically, the idea here is to come up with lab results that are based on evidence. So we have the scientific method, which consists of a theory or a purpose, whatever the purpose of your research is, and then you're going to generate a hypothesis based on something that you observe or something that you think is true, basically a prediction. That's usually an if-then statement. If I manipulate this variable, then this will be the result. So the independent variable and the dependent variable. You do your actual lab experiment, which should be ethical, but also should be correct and accurate. And that's your procedure to test your hypothesis. And then you analyze that data and come to a scientific conclusion. As we mentioned before, it can be problematic sometimes, especially in psychological research, because there are things that you cannot ethically or really even scientifically study in a lab setting at all. So there are other descriptive research methods that psychologists would use in order to come up with psychological findings. Those are going to be things like surveys, case studies, correlational studies that come from either survey data or compiled research. You have naturalistic observations. There are various ways that psychologists can come up with this data. So we'll explain the difference. Oftentimes, people confuse survey data, case study data, naturalistic observation, and they don't really know what the difference between a naturalistic observation and a case study is, and so we'll get into the details there. So the thing that we have to think about when you gather large amounts of data. Large amounts of data is susceptible to bias. For instance, if you go online and you want to read Yelp reviews of restaurants, you're going to get something that's known as volunteerism bias. And volunteerism bias is just one type of bias that's really difficult to avoid, that's based solely on what we call an unrepresentative sample. So for instance, if you go and you look at a restaurant review, most of the people who are willing to go online and do reviews of restaurants are either because they had a horrible experience at that restaurant or because they had a great, phenomenal experience at that restaurant. They don't really have a mediocre experience to report. So because of that, that's known as volunteerism bias, because it refers to the data that we have, or the sample that we have, is solely based on people who volunteer to participate in that survey. So there's all kinds of bias that comes up in different samples. And so there's things that you can do as a researcher to try to eliminate bias. And that's the goal. If you get that in an FRQ and they ask you how to eliminate confirmation bias or hindsight bias, volunteerism bias, survivorship bias is one type of bias. How do we eliminate bias? That's by having a representative sample. And a representative sample is a large enough sample size. So that's one way that you could explain that in an FRQ. The sample size is large enough that it's probably representative. But there's another way that we can look at representative samples, and that's by random sampling. Random sampling is an important term that you need to know. It refers to survey data. It's not experimental data. Experimental data, those are people that are being chosen or assigned randomly to the experiment group or the control group. So random sampling is to survey or correlational data, as random assignment is to experiment. So the population refers to all of the people who have an equal chance of being in your study. So if you're doing a lab experiment and 15 people volunteer, then the population that you're randomly assigning into the control group or the experiment group are those original 15 people, because they all had the same equal chance. The population of a survey that you do in the mall is all of the people who were in the mall at the time that you were conducting the survey. They had an equal chance. So population is not everybody that participates in your research necessarily. It's all of the people who had the opportunity to participate in your research. So if there's a survey that's done on a college campus, the population would be all of the students who were on campus during that time that the survey was being conducted. And that obviously cannot be representative sometimes, because you do not have a diverse population of age groups. You may not have a representative sample of racial data, and you may have a misrepresentation of various categories. So to randomly sample means to choose every third person or every fifth person, every 10th person, and you still may not get a truly representative sample. If your sample size is small, even if you randomly sample people, you might get 90% of the people in your survey are white, or 90% of the people in your survey are women, and you can't really manipulate that. So another FRQ tip for you is that if you get a question about how to fix an unrepresentative sample, the answer to that is to replicate the study. Replication is, so if we get an unrepresentative sample, we have to replicate that study or replicate that data again using random sampling and random assignment, and then we will hopefully get results that are a little bit more evidential. So correlation versus causation. This is another interesting topic. When you look at things that are not studied in a lab experiment, right? So let's say, for instance, naturalistic observation. Naturalistic observation is different than something like a case study, because in a naturalistic observation, the subject that's being studied is not aware that they are being studied. That's the key. So we can use that to gather a lot of information, but there's still some flaws in the scientific process there. So naturalistic observation is when a subject does not know they're being studied. A case study, on the other hand, people are willingly participating in that. It doesn't necessarily have to be one person. Sometimes it is only one person, but it's a unique case. It's something that's not common or is unethical or impossible to reproduce in a lab. So when we get into the biggest forms of data, we're looking at things that are statistical. And the problem with statistics is they have flaws. Again, we talked about bias, but there's also the correlational flaw. And the correlational flaw is a phrase that you've heard a lot. That correlation never means causation. It just suggests that there might be a relationship. So a correlational data is when we take two different variables and plot them on a scatter plot. And the idea behind a correlational study is to gather a large enough sample size so that you can predict. So that's the key there, prediction. Correlational studies are for predicting behavior, right? But there's a problem with predicting behavior based on correlational data. So we'll look at the first cartoon as an example why. It says another huge study found no evidence that cell phones cause cancer. What is the WHO thinking? I think they just got it backward. Okay, and what they're talking about is a great example of correlational flaw in this idea that when you plot people who have cancer against people who have cell phones, you see a strong correlation between the two. And it's a silly example, but if you look at all the people who have cancer who also have cell phones, that was used as a scientific basis to suggest that cell phones caused cancer, because the statistics showed that there was a huge percentage of people with cancer who had cell phones, had cellular phones. So to make it comical, you look at the last scene there and it says there are so many problems with that. And just to be safe, until I see more data, I'm going to assume that cancer causes cell phones. So again, correlational data is not necessarily that one thing causes the other. They just happen to correlate and they are instances of variables that happen alongside one another. And it's usually because of something else entirely, right? And so this example would not, maybe there's no connection between cell phone use and cancer. There is a statistical prediction that people who have cancer probably have cell phones, but it doesn't work to say that the cell phone was the cause of the cancer just because the cell phones were there, right? So another example is the ice cream example. Very famously, there was this data was compiled years and years ago by someone who was trying to explain the correlational flaw, and they said if you take two variables that occur at the same time, you can get problematic findings, right? Things like the correlation between ice cream sales and shark attacks. So if both ice cream sales and shark attacks increase when the weather is hot, they're not caused by each other, they're caused by a third factor, a confounding variable, which in this case is the hot weather. So lots of people go to the beach and they eat ice cream, and they're also more likely to swim in the ocean, which obviously is where you are bit by a shark. So it's not just because ice cream sales and shark attacks correlate very strongly, as they obviously do, the data is not incorrect, but the prediction that you're more likely to get bit by a shark because you bought ice cream is statistically true, but it is not scientifically predictable as a valid outcome. It's not a lab experiment. You can't go into a lab setting and use those two variables against a control because it's just not ethical to do so. But you would easily find, obviously, that ice cream does not cause shark attacks or vice versa. They just correlate together. So that's the problem. If you've heard that phrase a bunch, correlation does not equal causation, that's what they mean. There's usually a third or sometimes multiple confounding variables that also lead to that same outcome, like money equaling happiness. Well, it's not that people have more money and they're more happy. I mean, they might be, but it's usually the things that they buy with their money that makes them more happy, and it's usually the better the health care that they can afford that gives them a better quality of life, and the nicer neighborhoods, and the lower crime, and the lower stress, and so on and so forth. So those are called confounding variables. So we can predict that people who have more money are more likely to be happier, and we can predict that happier people might be more likely to have more money, but it may not be a cause. So single-blind and double-blind studies. To go back to experimental design, you have the lab experiment itself, and let's look at a single-blind study versus a double-blind study. So a single-blind study, you have participants who are involved in the study, and they don't know if they are in the experiment group or the control group. So that's the most scientifically valid way to conduct a study. If you want to see if a certain anti-anxiety medication works, then you're going to give a blind test against a placebo to see if the outcome is the result of the people who took the pill itself or people who took what they thought was the pill, and that's just a placebo. And that's, of course, known as the placebo effect or the expectation effect. If we tell you that what you're getting is migraine medicine and your headache goes away, it might be subconsciously because you believed that you were actually taking migraine medicine when in reality you were just taking a sugar pill or a placebo. So that's a single-blind study where the participants are unaware whether they're in the control group or the experiment group. And to be fair, in every scientifically valid study, you're going to have at least a single-blind study. But to eliminate all bias, you can do what's called a double-blind study. And a double-blind study is when you have people who are helping to conduct the experiment, and those people who are helping to conduct the experiment also are quote-unquote blind to which is the placebo and which is the experimental drug or the experimental treatment. So neither you, being the participant, nor the experimenter who's actually conducting the study knows which treatment you're receiving. And a lot of people get confused by this. Obviously, somebody knows which is which, and so that's why it's a funny cartoon there. It's not, you would never be able to find scientific findings if no one was aware. So maybe you would number the cups of the liquid medicine that you were given, and the odd numbers would be, or the every third number would be the drug, and the other ones were the placebo. But the person who's actually administering those trials in that lab setting would not know which was which. That's what they mean by double-blind study. So if you look here, they use the term study manager. You have pill A and pill B, you have the physician, you have the patient, and then basically the random allocation of treatment. So basically you have a representative sample, you have people who have been randomly assigned to either the experiment group or the control group, and in some cases you don't even know which one they are. You just randomly number them. You're 1, you're 2, you're 3, you're 4, and then every third person gets the drug. So you don't even know which person is going to get the drug going into the study, because that also would eliminate bias. Variables, and it's important to know the difference between the variables, and these are often confused. So lock in for the difference between these two variables real quick. The independent and the dependent variable refer to a lab experimental setting. The independent variable is what a scientific researcher or a psychologist is manipulating in order to get an outcome. So the independent variable is called the independent variable because it stands alone by itself. It should cause an outcome. It should not be the result of an outcome. So in the case of the example we used before, if we're administering a drug, the independent variable is the drug. It's not the result. The drug didn't fall out of the ceiling and appear. It's not a result. It is what we're adding, administering, changing, manipulating, if you like that word better. The dependent variable is the result, because it should be dependent upon whether or not we change something. So even if it's not drugs in a lab setting, what if you did a field experiment on yourself? What if you wanted to see if you did better on an AP Psych test when you studied an hour before the test versus your normal night before? Well, if your night before is your traditional routine, well, that's going to be your control group. That's what you're going to compare your results to. So you know how you do when you study the night before. And let's say the first 8 tests of the school year, you studied the night before. That's your control. Well, you're going to change that now. You're going to manipulate that. So the variable that you're manipulating is the time of day that you study. Now you're going to study an hour before in the morning, before you go to first period, and then you take your test, and the dependent variable should be the result. It should be the change. So if changing the time of day of when you study for a test does not result in a different test score, then we can conclude that your hypothesis is incorrect. You're not doing poorly on the test because you're studying at the wrong time. It may be something else entirely, and that opens up new hypotheses, like maybe you're studying incorrectly, maybe you're not studying for enough time. There's other possible explanations. So the independent variable is what we're changing in order to get the outcome. The dependent variable is the outcome. That is the result. So if you want to look at a hypothesis backwards, right, remember we have an independent and a dependent variable. If blank, then blank will be the result. If you want to look at the hypothesis backwards, it makes more sense. Okay, the result, the dependent variable, okay, the result is dependent upon what we change. So if I study an hour before the test, then I should get a better grade. That's a testable hypothesis. The independent variable is when you study. The dependent variable is whether or not you get a good grade. So you can easily test that against the control, and you can get a scientific finding. In other words, you can identify cause and effect. That's the goal of experimental studies. Okay, somehow we have magical flashing going on. So other statistical categories would be measures of central tendency, and this is going back again to correlational studies. This is going back to survey data. This is when you have massive amounts of data in your sample size. You're going to plot things like the mean, the median, the mode, and the range. And all these things matter. The mean is going to be the average. But if you only have 10 people in your study, the average is probably not going to be extremely telling, scientifically speaking. So the median is going to matter, right? So for instance, you may have surveyed 10 people in your study, and one of them makes $10 million a year. Well, that's going to throw off your mean. You know, out of those 10 people in the study, the millionaire is going to drastically improve the mean. So the median comes into play here, the middle number of the sequence. So this person may be an extreme, right? If you look at test scores, we always call the curve breaker in your classes, the person that gets the 98 on the test and breaks the curve. So you have the extremes on each end of a bell curve, and that's why it's not just the mean or the median. You also have to take the mode and the range. So the number that occurs the most, right? So the average score on a test in your class might be a 74. Well, what was the range? Well, the lowest score might be a 58 and the highest score might be a 94. Well, that's your range. That's the highest and the lowest. That's the difference between, and the mode is going to be the highest occurring. So the median matters and the mean matters, but when you have a small sample size, the mode and the range can tell you more. When you get all of those things that are the same, when the mean, the median, and the mode are the same, you get a bell curve. The range is what it is. The range is not going to change. The range is the lowest and the highest. And a lot of people have gotten that wrong on tests in the past. Don't get hung up on the range. The range is not something that, it's just going to indicate where the extremes are. The range is not something that you would say is being changed as a result. It's more like the mean that's going to be changed, or the mode that's going to be changed. Ethics and Studies, this is from the American Psychological Association, or the APA's ethical guidelines for experimental research. Again, ethics are a barrier to scientific studies. And I know that sounds horrible to say, but that's why we have other types of data. You have correlational data, you have case studies, you have naturalistic observation, and all of them have different times where they would be used. So for instance, if there was an ethical reason why we couldn't conduct a lab experiment, we would have to gather that data another way. So for instance, you might say that people who are the victims of childhood physical abuse, they turn out to be abusive in their adulthood. Well, you would want to know the answer to that, but you can't ethically, nor would you morally want to test that. It doesn't mean that you don't need to know the answer scientifically. So that's when when ethical concerns come up, the other forms of research come in. That's why you would do a correlational study instead of an experiment, not just because the data size is bigger, but because it's not ethical or impossible to test. For instance, you want to know if money causes happiness. Correlational studies don't give you a cause, they give you a correlation. Well, you can't ethically study by manipulating the amount of money that people have. It's also unethical to manipulate the amount of happiness that people experience. So that's not something that can be realistically tested in a lab. So there are those biological purists who have always critiqued psychology as a pseudoscience because not all of the psychological theories and findings, so to speak, are based on lab experimentation. But in the defense of that, even though that might be a true statement, it's not possible to test everything psychologically that you would want to know in a lab setting. You can't test it against a control group, or you can't test it ethically, or in some cases it's not even possible to test it. You can't test your dreams, we can't manipulate certain things in your cognitive processes, but we still want to know the answer to that. So when it comes to whether or not you can experiment on something like drug abuse and success in life, we could physically and scientifically test that pretty easily in a lab, in a longitudinal study against a control, but it's unethical. So ethics are there for a reason, so that the means don't justify the end. For instance, a good example of ethical violations would be looking at things like the Nazi experimentation that went on in concentration camps. So if you could argue that scientifically speaking, those horrendous experiments that went on were justifiable because we got life-changing and scientifically changing data from that experimentation. Well, that's very problematic, because if a scientist can justify that the means of research the end justifies the means of research, then what's to stop them from harming other people in the name of science? So there are certain things that the APA came up with as the guidelines for ethical research. And a lot of the studies that we've covered over the course of the year fall in the category of unethical, or they have been a violation of APA ethical guidelines because those experiments took place before these guidelines existed. And ethics are different than laws. Ethics basically are the standard of business in a certain field. It's just things that are not done. So your results can be thrown out or rejected by your peers if you do something unethical. So for instance, in order for something to be scientifically valid, it needs to pass peer review. So when you publish a scientific finding based on a lab experiment that you conducted, it's going to be reviewed by your peers. And if it commits ethical violations, your peers are not going to review that in a way that's favorable, and the scientific community is going to reject your findings. And so you can't just ethically, not to mention the fact that you're not going to get any funding from a research board, an internal revenue board, when you state your hypothesis and it has ethical flaws in it. So looking at the APA ethical guidelines, you have a page in your notebook for this, a printout that I gave you early on in the year, so it's very easy to find it. But basically it has to do with informed consent, protection from harm, that's physical and psychological harm, confidentiality, and debriefing if deception is used, right? So another one that's not listed there is freedom to withdraw. That's another APA ethical guideline that has to be adhered to. So informed consent, basically you have to get consent from people in order to participate in your study. So doing a field experiment that's a naturalistic observation where you drop a wallet in the middle of a busy street to see who takes it actually probably falls in the unethical category, because those people are not informed of what they're being tested on. It's a naturalistic observation. They did not give their consent to be in the study. But to be fair, sometimes to get positive results, you have to deceive people. So in those instances when you deceive people and you don't tell them the nature of your study or the nature of your hypothesis, you have to debrief them after the study is over. And where the informed consent comes in naturalistic observation is if those people are offended by your research tactics and they don't want to be included in your results, you ethically have to omit them from your data. So if somebody does something in your study and then finds out when you debrief them that they were deceived and they didn't know the true nature of the study, they can choose to be withheld from your data. So that would be the ethical correction of informed consent. A lot of the times on the AP exam, they're going to ask you to not only identify the ethical flaw, but they're going to ask you to suggest ways to fix the ethical flaw. So that's where you're going to have to be smart and look at how it's phrased in the FRQ, and it'll say something like the results of the study were published with Tim's name in the newspaper, and you'll have to know, well, that's an ethical violation because it violates Tim's confidentiality. Now, if they ask you to suggest ways to fix the ethical flaw, then you would say the ethical flaw of confidentiality could be fixed by using a number instead of Tim's name, something like that. So just be aware of that when you're writing your FRQs, whether or not they're asking you to identify the ethical flaw, which is a very common question, or if they're asking you to actually correct the ethical flaw in the study. So that wraps up Unit 2. We will get into Unit 3 in our next video, and that'll be coming soon, so stay tuned.